Alright guys, so this is the first of two videos that are going to be a part of the first assignment for after spring break. In this video we are going to be going through and sort of reminding ourselves about the two conic sections that we talked about before break, parabolas and ellipses. And this is largely going to be from your notes. I'm going to have additional problems that I'm going to attach with a separate sheet to the assignment. But largely right here, you've already taken notes on the parabola and the ellipse, and this is just going to be a video that reminds us about what we talked about. And the last video is going to be on that last type of conic section that we didn't quite get a chance to talk about, hyperbolas. So what is a conic section? Well, a conic section is a shape that we get by cutting a conic, which are these two cones placed end to end with a plane. And if we cut into one of the two cones with a plane that doesn't go through a cone, then we get the parabola shape, right? If our plane goes all the way through the cone, we say we get an ellipse. And if the plane cuts perpendicular to the cone, we can say that ellipse is a circle. If our plane cuts through the top cone and the bottom cone, we get what we call the hyperbola shape here. So right here, we're just going to go through and remind ourselves about the equations that define these conic sections on the xy axis. We need a little bit of vocabulary first. Right here we said that when we define the parabola as a shape, we use a locus definition. And the locus definition of the parabola is the set of all points that are equidistant from a line, the directrix, and a point not on that line, the focus, right? So right here we have our directrix, this line right here in green, and we have our focus, which is this point, and that's not on the line. And we can say that the parabola is going to be the collection of all points that are equidistant from the focus and the directrix, right? The vertex of our parabola is the point that minimizes that distance from the focus and from the directrix. We say that the focal length is the distance from the vertex to the focus, and that's this length right here, from the vertex to the focus. And right here, since we're saying that this distance goes from the vertex to the focus, we can think about this distance as being positive or negative depending on the orientation of our parabola, right? We would say that the directrix is, of course, going to be a length p away from the vertex in the opposite direction. In other words, these two lengths obviously are the same, and that's, of course, how we've defined our parabola. We say that the focal axis is the line through the vertex and the focus. We can also think about this as the axis of symmetry. And we say that the focal width is the width of the parabola through the focus, and that would be this length right here. And because this is a length that is not necessarily defined going from one point to another, we're going to say that this length is always positive, right? We said that a parabola as a conic section on the xy axis with vertex hk can be defined vertically with the equation x minus h squared equals 4p times y minus k, right? And horizontally as y minus k squared equals 4p times x minus h. Now, within this equation, we're seeing that focal width 4p, but within the equation, that 4p can be positive or negative, and that's going to tell us whether the focal length p itself is positive or negative, and that's going to help us determine how we're orientated vertically and horizontally, right, when we're going from our vertex to our focus. So our two equations that we graphed, or we were looking to graph before break, we graphed our first one, A, and we didn't graph B. We'll go into that next. But just to sort of go back through this, immediately we can see that because it's the x expression that's being squared, we know that our parabola is going to open vertically, either up or down. And right here we can take the vertex, where we've got 2 being added to x, And so right here we know that the x value of our vertex is -2, and right here we don't have anything added or subtracted from y, and so we can say that the y value of our vertex is going to be 0. And that gives us our vertex right there as the ordered pair -2, 0. Now right here we can take that coefficient multiplying the y expression, which in this case is just y, and set it equal to 4p to determine the focal length. Right here, when we set 4p equal to -8, we get p equals -2, which means that we are going down from our vertex to the focus. So right here, -2 is the length p, and that means we're going down to the focus, right? And that would mean that we're going backwards up to the directrix, right? So we can graph both of those pretty quickly. Now, after that, we've basically gone through and graphed the vertex, the focus, and the directrix. We can use the focal width, which we have within the equation right there, to get a quick graph of our parabola. So right here, from the focus, we're basically going to be going out 4 in either direction to give us that focal width of 8. And right here, with those 2 points and our vertex, we can go ahead and graph our parabola opening down around our focus like that. Now, for example B, since it's the y expression that's being squared, we can see that our parabola will open horizontally. Right here, we can similarly pull the vertex pretty quickly from the equation of the parabola. Right here, we can say that since we're adding 4 to x, we know the x value of the vertex is going to be -4, and since we're subtracting 1 from y, we know the y value of the vertex is going to be 1, so we've got a vertex of -4, 1 right there. And we can go ahead and get that focal length by taking the coefficient that we're multiplying the x expression by 6 and setting it equal to 4p. So right here we can say 4p equals 6, and that gives us a focal length of p equals 1.5. Now that's a positive 1.5, so that means that we're going to be going 1.5 horizontally in the positive direction to get our focus. And that will give us the focus as -2.51, right? So there's the ordered pair of the focus. Right here we can go that same 1.5 in the opposite direction to get our directrix. So if we go 1.5 in the negative direction, we will get our directrix as the line x equals -5.5. And right here we can take that focal width of 6 and get 2 points on our parabola to graph the parabola with the vertex. So right here we would go out 3 in both directions from the focus, and that will give us the focal width of 6 through the focus. And right here we can graph our parabola through those 2 points and the vertex looking something like this. All right, so on the attached sheet, we've got 2 questions for you to look at. I want you to sketch a graph of the parabola with the focus and the directrix. So right here, we're basically giving you the equation of a parabola as a conic section on the xy axis, and I want you to go ahead and graph that guy. And I want you to plot and give me the coordinates for the focus, and go ahead and plot the directrix, draw that directrix, and give us the equation for the line of the directrix. On the second problem, I'm asking you to look at the graph of the parabola as a conic on the xy axis with the given focus and directrix, and come up with an equation for that parabola as a conic section on the xy axis, right? So right here, we can see that this is opening horizontally, so we know it's going to be some y minus k squared equals 4p times x minus h, right? And we would basically want to pull the information that would allow us to fill in the k, h, and p values here for this equation. All right, guys, so I want you to pause the video here and take a look at these. All right, guys, so going through this first one, we are going to graph the parabola defined by the equation x minus 1 squared equals 4 times y plus 3. Immediately we can pull the vertex from the constants that we are adding and subtracting to x and y. And right here we have our vertex as 1, -3, so we plot that guy right there. And then we have our 4p as 4, so right here, solving for the focal length p, we get 1, and that means that we are going up 1 from the vertex to the focus, since our x expression is being squared, and we know this is going to be a vertically orientated parabola. So right here, that gives us the focus. Then we're going to go that same distance in the opposite direction to get the directrix, which will give us our directrix as y equals -4, our focus as 1, -2. And then right here, we can sort of take that focal length of 4 and basically get 2 points on the parabola on either side of the focus, and then our parabola will be drawn through those 2 points and the vertex. And that is the graph of our parabola. Okay, so this next one was a little bit trickier. We had to sort of use the information that our graph gave us to come up with the equation for the parabola. So right here, we've got a focus of -1, 1, and we've got a directrix of 2. Now what that gives us is the distance from the focus to the directrix through the vertex is 2p. And basically right here, I'm going to take that as a positive value. I'm going to say that we have the distance from the focus to the directrix as the absolute value of 2p, and we can sort of see on the xy axis that that's a length of 3. Now, because our parabola is opening negatively, we know that that p-value is going to be negative, since that p-value is the distance from the vertex to the focus. We know that we're sort of going backwards on the x-axis there. And so that tells us that our 2p is actually going to be a -3, which tells us that p is going to be -1.5. So if we go back 1.5 from our focus, we get our vertex as 0.51. And right here, we've got all the information we need. We can basically plug in the x and y value of our vertex into our equation as the h and the k. And then actually right here, we can say that our focal width is going to be 4 times our -1.5, giving us a -6. So this is the equation that will define that parabola. All right. When we look at an ellipse, if we're defining it as a locus, we say that it is the set of all points whose distance from 2 points, the foci, have a constant sum. So with an ellipse, we have 2 foci. Now, we're not going to look too much at this locus definition anymore. We talked about it in class. But in general, right here, what we do want to do is view the vocabulary and the terms that we're going to use to define the equation of the ellipse on the xy axis. So right here, we have the focal axis as the line through the 2 foci. And we say that the major axis is the largest diameter. And we say that the major axis is on the focal axis. And we say that this major axis is a length that we're going to call 2a, right? So this whole length is 2a. And we say that the vertices, of which we also have 2 for our ellipse, are at either end of the major axis, or this largest diameter. Now, if we know that the entire major axis is 2a, then we can say that half the major axis, or the distance from the center to our vertices, would be a length a. We say that the minor axis is the smallest diameter, and right here we say that that smallest diameter has a length that we call 2b. And right here, again, if we have the entire minor axis as 2b, the distance from the center to the perimeter of this circle along that minor axis is going to be a length of just b. We say that the distance from the center to the foci is a length that we call c, right? So these are the 3 major lengths that we're going to use to define the equation of our ellipse on the xy axis. Now, The thing that we said in the end here was that if we went from one of the foci to the end of the minor axis, that length right there was A. And that gave us a Pythagorean relationship within the ellipse, right? We'd say that B and A are perpendicular, right? Or the major axis and the minor axis are two perpendicular lengths. And right here we have a Pythagorean relation with lengths C, B, and A, where the hypotenuse of the right triangle within the ellipse is the length A, and the two shorter sides are B and C. And that gives us the Pythagorean relation for the ellipse as A squared equals B squared plus C squared, right? And we're going to use that to help us find the dimensions of our ellipse when we're graphing it on the XY axis. Right here, we said that the ellipse as a conic on the XY axis with center HK is given to us horizontally orientated with the equation x minus h squared over a squared plus y minus k squared over b squared equals 1, and vertically orientated as y minus k squared over a squared plus x minus h squared over b squared equals 1. Now, right here, since we're adding the two terms in the equation that's defining our ellipse, really, these two terms are interchangeable since addition is commutative. We can add in either order, right? So what's going to distinguish the horizontal orientated ellipse from the vertical orientated ellipse? And that's going to be that we know that A is larger than B. So right here, what we can say is the term that has the larger denominator determines the orientation of the ellipse, whether it's going to be horizontal or vertical. If we're looking at our first example that we graphed in class, we've got x minus 3 squared over 25 plus y plus 2 squared over 9 equals 1. Right here, because the x term has the larger denominator, that means that we are a horizontally orientated ellipse, and the a value is 5, and the b value is 3, since our a squared is 25 and our b squared is 9, right? So right here immediately we have that distance from the center, the perimeter of the ellipse, at the ends of the major axis and the minor axis with that a and b value. And right here we can take the center from the constants that we're adding and subtracting from our x and y. We can say here that our center for our ellipse is going to be 3, negative 2, right? And right here we can basically go out a length of 5 horizontally, since we know this is a horizontally orientated ellipse, right, with a larger denominator under the x. So right here we would go out 5 from the center to get the two vertices, the ends of our major axis, and we would go out 3 vertically to get the points at the end of the minor axis, right, which are going to be on the perimeter, and then we can draw our ellipse through the vertices and the points at the end of the minor axis and get the ellipse that we're seeing right here. Now, if we also want to graph the foci, we basically need to know that length c, right? Well, we have that Pythagorean relation, which is a squared equals b squared plus c squared for an ellipse. And right here, we can take a squared as the denominator of our x term, and we can take b squared as the denominator for our y term, and plug those in and solve for c. We get a c length of 4, and so right here we will go out a distance of 4 to our two foci, right? Now, in general, what I would say is, if you're looking to determine the ordered pair for the vertices and the foci, it's almost easier to graph first and then identify those ordered pairs after you graph. So right here, I've gone through the process of graphing this ellipse with its foci, and now right here, I can go ahead and determine what those ordered pairs are, rather than try to add and subtract quantities from the center itself to determine what those foci and what those vertices would be. All right, so right here, let's take a look at this next equation. Right here, we can tell immediately that this is a vertically orientated ellipse, and we know this because the denominator of the y term is larger. So right here, we can say this is a vertically orientated ellipse, and we have an a value of 6 from our 36, which is a squared, and a b value of 2 from our 4, which is our b squared, right? We know that the center of this vertically orientated ellipse is going to be given to us by the constants that we're adding and subtracting from the y terms. Right here we can say that our center is going to have an x value of -2, and since we're not adding or subtracting anything from y, we can say that the y value will be 0. So right here, there's the center of our ellipse. Now right here, since we are vertically orientated, we are going to be extending that length a up and down to get the vertices. So right here we go 6 up and 6 down to get the vertices, the end of the major axis. And then right here we're going to go 2 out to get the ends of the minor axis horizontally, and that gives us the ellipse that we've got right there on the xy axis. So right here we've got the vertices, ends of the major axis, largest diameter, and we're also going to determine the foci. Now right here again I'm going to say that I know the Pythagorean relation for the ellipse is given to me right here. And right here I can say that my a squared is 36 and my b squared is 4. So right here I know that I've got 36 equals 4 plus c squared. And that gives me c as, right here, the square root of 32. And I can say that that number then is approximately 5.7. So I'm going up 5.7 to one foci, and that's going to be about right there, well, pretty close to the vertices. And then down 5.7 to the other foci, and again, that's really close to the vertices. This is tough to draw, but right here we can approximate a little bit and get those foci right there. All right, guys, so on your attached sheet, you're going to go ahead and try to graph an ellipse from the equation that we've got right here. And you're going to come up with the equation for an ellipse with the given vertices and foci, right? So it's a lot like the problems that we looked at for the parabola on the previous questions. Right here, what I want you to do is to go ahead and give these two guys a shot, and we will come back and look at them in a second. All right, guys, so looking at this first one, let's see that the x term has the larger denominator, so we know this is going to be a horizontally orientated ellipse. Right here, that gives us the a value of 4 and the b value of 2. We can pull the center from the equation. Right here, we've got x plus 1, so that means the x value of the center is going to be -1, and we're not subtracting anything from y, so we've got a y value of 0, giving us our center as -1, 0 right there. Now right here, we can quickly graph our ellipse by just getting the ends of the major axis and the minor axis by just going out 4 horizontally for the ends of the major axis and out 2 vertically for the ends of the minor axis, right? And then sort of draw our ellipse through that. Right here, we also want to graph the foci, though. And so right here, we're going to use the Pythagorean relation, a squared equals b squared plus c squared for an ellipse. And right here, we can say that that Pythagorean relation is going to be 16 equals 4 plus c squared, which gives us c as the square root of 12, or approximately 3.5. So we go out 3.5, again, approximately. This is not perfect, but 3.5 from the center to get the 2 foci. And again, right here, this is where I would go ahead and get the ordered pairs for the vertices and the foci after I've already plotted this stuff, because it's a lot easier to just read it off the graph. Right here, we've got vertices of -5, 0, 3, 0, and foci of -4.5, 0, 2.50. And again, the foci are approximate. So right here, looking at this next one, we're coming up with an equation for the ellipse that we've got. Now, immediately we want to get the center. And we can get the center by using the vertices of the foci, since we know that the center has to be halfway between the vertices, or halfway between the foci. So right here, we can say that our foci are 0, 0, the origin, and 0, 6. So that means that our center is going to be 0, 3, right? We've got that center right there. And we can immediately look at our ellipse and see that A value is 5 and that C value is 3, and that leaves us with B value that we have to determine. So using our Pythagorean relation, we can take A, square it, and get 25, and say that that would be equal to B squared plus our C value squared of 3. So right here, that gives us 9. So right here, solving for B, we get B squared as 16 and B as 4, which is what it looks like on the graph. Now in general right here, we're really going to just use B squared in the equation. We know that this is a vertically orientated ellipse, so that means that the A value squared is going to be the denominator of the Y term. So right here we've got Y minus 3 squared divided by 25 plus X squared divided by 16 equals 1 for this vertically orientated ellipse. All right, so that's the end of this video, and we will take a look at hyperbolas in the next video.